finally, the final unit. 610 is conservation of energy. And there's not really anything new here since we've already talked about conservation principles. I already saw conservation of energy or conservation of momentum. And we already know about potential energy and kinetic energy. It's just putting that together. So when you're solving physics problems with energy methods, you have to look at the situation and decide what types of energy you have at the beginning and at the end of the problem. And so in general, the sum of the energies initially equal the sum of the energies finally. Okay? So the initial energy in the system equals the final. It's conserved. With some energy we changed over to thermal or vibration or heat energy in some cases like that, and many times we call that lost energy, but it's just a conversion to heat. And in some of these problems we ignore that and look at just like changing from potential energy to kinetic energy. So for most of these problems we assume mechanical energy is conserved, but in truth it rarely is. Sound, vibration, heat, etc. results in a loss, but the loss is really just the conversion over those different types of energies. So let's look at one where mechanical energy is conserved. So an example. So a water balloon is dropped from 6 meters above the ground. What is the speed when it reaches the ground? So the sum of the energies initially equal the sum of the energies finally. And so for this case, we have all potential initial and all kinetic final. Okay? And the formula for potential is mg delta h, and the kinetic energy is 1/2 mv squared. And so that becomes important because you notice we're not given a mass here, and that's going to fall off there. So g is 10 meters per second squared, h is 6 meters, 1/2 v squared. So 60 meters squared, second squared equals 1/2 v squared. Bring the 2 over. 120 meters squared, second squared equals v squared. So v is the square root of that, which is square root of 120. The speed will be 10.95 meters per second, and of course that's down. Now, we could have done that problem in an old method, right, using an Atwood machine, where we just fill in a simple, I'm thinking ahead, not an Atwood machine. I'm thinking ahead to the next problem in my head, sorry. Well, we could do a simple easy chart here, the RGC, and in that case we started at 0. We're wondering what we end with. We know our A is -10 meters per second squared with a distance of 6 meters. And we would do, to get that speed, Vf squared, Vi squared plus 2a delta S, Vf squared with 2 times -10 times 6 meters, and of course that's Vf squared is equal to, actually it's -6 meters because it's falling, 120, and of course that's going down at -10.95 meters per second. So you get the same answer either way. Sometimes it's easier to use energy methods. Sometimes it's easier to use the simple kinematic mechanic equations. Okay, now the Atwood machine. It's created from a 10 kilogram block and a 15 kilogram block. What are the speeds of the block after the 15 meter block has fallen 4 meters. Some of you did this using RGCs and a stopwatch and stuff when you were doing it for a lab. But now we're going to do it using energies. Now, the sum of the energies initially equal the sum of the energies final. Now, it's 4 meters up, but we're not considered like we just consider that like level ground, but that the blocks are still moving at that point. So the 10 kilogram block is not up at all. Initially, it's not up from 4 meters at all, and neither of them are moving. So looking at them to start to, you can see that it's all in the potential energy of the 15 kilogram block initially. And that's going to equal the, once it starts to fall down and move to a new state, and the new state would look like this, where the 15 kilogram block has moved down, and the 10 kilogram block has moved up. We can see that it's going to equal the now 4 meter up 10 kilogram block. So the potential energy is that. Okay? That's after. There's no potential energy of the 15 kilogram block left, but they both have kinetic energy, so there'll be a K10 and a K for 15 because both the blocks will be moving. So that total energy initially, the potential energy of the 15 kilogram block must equal all three of these after. So we could see initially we have 15 kilograms times 10 meters per second squared times 4 meters, which is 40 times 15, 600 joules on this side. That would equal the U10, which is going to be 10 kilograms times 10 meters per second squared times 4 meters, or 400 joules. One half times they're both moving at the velocity squared. Mikhail just interrupted me, which is why I got thrown. But anyways, and then the 1/2 of 15 kilograms times that v squared. They're moving at the same speed, so we'll use that. So solving this over, subtract the 400, we get 200 joules, and that equals 5v squared plus 7.5 v squared, which is 12.5 v squared. So v squared equals 16. So the velocity would be 4 meters per second. Okay, we'll do other problems as practice in class.